Your watch is lying to you. Time isn't fixed. On this planet, you'd celebrate New Year's Eve 3 times before lunch. Its surface is hotter than a nuclear blast. Its gravity is playing cosmic Jenga with its core. And scientists are calling it the Doomsday Clock Planet. This is Kepler-78b, rewriting everything we know about survival in space. By the time this video ends, it'll have aged 260 years. Let's begin.
Sometimes you find something out there in space that just makes you, stop and go, hang on a second.
Definitely.
And today, we're looking at one of those real cosmic curveballs, the exoplanet Kepler-78b.
Oh yeah, that one. It's a genuinely unexpected sort of planet. Imagine something about the size of Earth.
Okay, Earth-sized.
But it whips around its star every 8.5 hours, just incredibly fast. It certainly made astronomers sit up and take notice when it was found.
Absolutely. And this isn't some, huge gas giant miles away. We're talking a planet that's similar to Earth in size, even density.
Right.
But that orbit, it makes Mercury look like it's standing still. And what's really solid here is the data, isn't it? It comes from NASA's Kepler telescope.
Yeah, the transit data.
Plus really vital work from telescopes back here on Earth.
Exactly. Kepler, its whole job was finding planets by watching for those tiny, tiny dips in starlight when a planet crosses in front.
The transit method.
That's how Kepler-78b first popped up. But just seeing the dip doesn't tell you everything. To really know if it was a planet and what kind, we had to figure out its mass.
Okay, right. So Kepler saw this star, maybe 400 light years off in Cygnus, dimming slightly back in 2013. And it kept dimming really regularly every 8.5 hours, which immediately screamed super short orbit.
That's the transit signal, yeah. But like you said, just the dip tells you something is there and how fast it's going around. Maybe its size relative to the star, but not its actual mass.
Right.
To confirm it's a planet and get a feel for what it's made of, you need its gravity. You need to see how it affects its star.
And that's the ground-based part.
Yeah.
Using really sensitive instruments to look for the star wobbling.
Exactly. Looking for that tiny wobble, the radial velocity caused by the planet's gravity pulling on the star as it orbits.
Which must be incredibly hard for an Earth-sized planet. Their gravity is minuscule compared to a star's.
It usually is, yeah. That's what's so tricky. But Kepler-78b, it's relatively heavy for its size, and it's so incredibly close to its star.
That the gravitational tug, the wobble effect, was just barely measurable. Enough for 2 separate teams to actually calculate the mass.
Wow.
And that was huge, wasn't it? The first time getting both size and mass for a planet basically the same size as Earth.
A massive step.
Suddenly we could figure out its density, start to properly understand what these smaller worlds are actually like.
Precisely. And the numbers were fascinating. It's about 1.2 times Earth's radius. So diameter maybe 9,200 miles or so.
Okay, a bit bigger.
And the mass came out around 1.7 times Earth's mass.
So bigger and heavier. What does that tell us density-wise about its makeup?
Well, you put size and mass together and you get density. And its density is almost identical to Earth's.
Really?
Yeah, somewhere like 5.3 to 5.5 grams per cubic centimeter. Earth is about 5.5.
So that strongly suggests rock and iron, like Earth.
Exactly. Mostly rock and iron, silicate materials. It kind of hints that the basic recipe for building Earth-like planets might be pretty common out there, even if they end up in really bizarre places.
Okay, so the ingredients are familiar, but I suspect that's where the resemblance stops cold, given that crazy short orbit you keep mentioning.
You are absolutely right. That orbit changes everything. It's only about 0.01 AU from its star, maybe even a bit less, 0.009.
And AU being the Earth-Sun distance.
Right. So Kepler-78b is about 40 times closer to its star than Mercury is to our sun.
40 times. I can't even... what are the surface conditions like? It must be unbelievably hot.
Unbelievably is putting it mildly. Estimates are between roughly 1,900 and 3,000 degrees Celsius.
Wow.
That's what, 3,500 to 5,400 Fahrenheit. It's basically got to be a molten lava ocean covering the entire surface.
A lava planet.
Yeah, no stable atmosphere could possibly survive that. It's like a terrestrial planet dialed up to 11, heat-wise.
Just scorching. And being that close, surely it's tidally locked too. One side always facing the star.
Almost certainly. The gravitational pull at that distance would lock its rotation pretty fast. So yeah, one side in perpetual searing daylight.
And the other in darkness.
Well, darkness might be pushing it. Even the night side would probably still glow red hot from that heat.
Okay, so we've got this Earth-sized, Earth-density planet. that's basically a superheated lava ball whipping around its star. It's already weird. But the biggest question, the real puzzle is, how did it even get there?
That's it. That's the fundamental mystery. Our current ideas about how planets form, well, they struggle to explain Kepler-78b's existence in that spot.
Right. It seems impossible.
It really challenges our basic assumptions.
Okay, so what's the core problem? Why couldn't it just form there?
Well, think about a brand new baby star. It's much bigger, puffier, more spread out than it is later in life.
Okay.
If Kepler-78b tried to form in its current orbit, it would have been inside the young star.
Ah, and planets don't form inside stars.
Exactly. They need to form further out in the protoplanetary disk from dust and gas.
Right, that makes sense. So, okay, it must have formed further out and moved in, right?
Yeah.
Migrated.
That's the logical next thought, yeah. And planet migration definitely happens. But the way we understand migration, especially the kind that brings planets inward, it usually ends with the planet spiraling all the way into the star.
Not stopping neatly just outside.
Exactly. It's hard to get the brakes on, basically. Stopping it in such a tight, stable orbit, just millimeters, cosmically speaking, from destruction, it's really difficult to model.
So it shouldn't have formed there, and it probably shouldn't have been able to migrate there without falling in?
Pretty much. That's why you hear astronomers using words like mystery, abomination, even enigma. It really makes us think, okay, what are we missing in our models?
Is it possible it's just a total fluke? A one-off freak of nature? Or are there others like it?
That's a great question. And actually, no, it doesn't seem to be entirely unique. It's now seen as sort of the poster child for a whole class of planets.
Oh, really?
Yeah, they're called ultra-short period planets, or USPs. Generally, rocky worlds orbiting their stars in less than, say, 12 hours.
Less than half a day for a year.
Crazy, isn't it? And Kepler-78b was really important because it was the first USP where we got that solid mass measurement. That made it a benchmark, something to really test our understanding against.
So finding more of these USPs, does that give us any clues about how Kepler-78b ended up like this? Does it suggest a common pathway we just don't know about yet?
It strongly suggests there are ways to make these things, yeah. We just haven't figured them out yet. Maybe it involves specific conditions in the early disk, or perhaps complex gravitational dances between multiple planets.
Pushing one inwards while others move out.
Something like that. It's an active area of research. Having Kepler-78b so well studied gives theorists something concrete to aim for with their models. Any new idea has to be able to explain this planet.
It's wild how one little planet can push science like that. Okay, so it exists somehow, but living on the edge like that, what's his future? Can't stay there forever, surely.
No, sadly not. Those immense tidal forces, the gravitational stretching and squeezing between the star and the planet, they're constantly at work.
Pulling it closer.
Relentlessly pulling it closer, bit by bit, over millions and billions of years.
And eventually?
Eventually, it's doomed. Either the star itself will age, puff up into a red giant and just swallow it.
Right.
Or maybe even before that, the tidal forces will become so strong they'll just rip the planet apart, shred it.
Grim. How long does it have?
Current estimates suggest maybe around 3 billion years, which sounds like a long time to us.
But cosmically speaking, not really.
Exactly. It's a transient thing. We're catching it in a temporary, though spectacular phase of its existence. It reminds us that solar systems aren't static, they evolve, sometimes dramatically.
So beyond just being this incredibly weird object, what's the big picture value of studying something like Kepler-78b? Why care about this doomed lava world?
Well, several things. First, it's absolute proof that planets the size of Earth, made of rock and iron, do exist out there, even in places we never expected.
Okay, point taken.
Second, figuring it out really highlights how powerful it is when we combine different ways of observing. Kepler finding the candidates from space, then ground-based telescopes doing the heavy lifting on the follow-up spectroscopy to get the mass.
The synergy.
Precisely. You often need both to really understand these planets.
And I guess it just paints a picture of the sheer variety of planets possible, right?
Right.
Even if this one is totally uninhabitable, understanding extremes helps define the whole range.
Absolutely. We're finding more of these lava planets now, studying them, maybe even looking at the light reflected or the heat they give off, tells us about geology under extreme conditions. It expands our understanding of planetary science overall.
So Kepler-78b, Earth-like ingredients, but in this completely alien, super fast, super hot orbit. Its origin is a puzzle, its end is a destruction. It's not just an oddball, it's actually teaching us a lot.
Yeah, it's forcing us to question our models, to think about processes we hadn't considered. How can the system exist? It's a fantastic scientific driver.
It really is. That aha. Or maybe, wait, what? Moment where one discovery challenges so much.
It's what makes exploring the universe so exciting, isn't it? You never know what you'll find next.
It really makes you wonder, doesn't it? If something as bizarre as Kepler-78b is out there, defying what we thought we knew, what other kinds of strangeness are waiting to be discovered? What other big questions about how solar systems form are just sitting there waiting for the right observation to unlock them? You know, just think about the sheer diversity of worlds that could be out there, challenging everything we assume.